And now we will finish off this mini chapter. So the natural log is the inverse of e to the x, and therefore it must look as follows. So if you imagine the exponential function written like this, we have to go, so these are negative values and these are positive values, so it has to look something like that. And if you think about it, it might take a while for you to think about it, and maybe we won't. And that means that the log looks like this. Maybe I'll just maybe show that with a little tiny example. So take a function from ABC. Actually, that's a bad choice. Let's say 0, 1, 2 to 0, 1, 2, and let us do f equal to, let's say 0 is sent to 1, 1 is sent to 2, and 2 is sent to 0. Okay, and if we graph it, and we say let's go 0, 1, 2 inputs, 0, 1, 2 inputs, the graph looks like 0, 1, 1, 2, 2, 0, something like that. Now if we turn it around the other way, so this initially is x and this is y, but if we turn it this way and now think of this as x and this is y, then if we write it this way, f inverse, well, it's going to be f inverse is what I'm saying. So this is 2, 1. This is 1, 0. Hope this works now. And this is 1, 2. Sorry, it's 0, 2. Okay, and if you look, remember the inverse is found by flipping these. So 0, 1, 1, 0, 1, 2, 2, 1, 2, 0, 0, 2. You see that by looking at the function like that, you get the graph of the inverse. So if this is the exponential function, turn it around like this, this is then the log function. So y is equal to log of x. And there's just really one point that we know about, which would be when x is equal to 1 with a log, you get out 0. So log of 1 is 0. Now this goes to infinity, but very, very slowly. Like if you think of this graph, it goes up really, really quickly in this side, which means that it does, like, as you take bigger inputs into the exponential function, you can keep doing that, but it grows really, really fast. And what that means is that this graph, if you look at it this way, it actually grows really slow. So this goes to infinity slowly, really, really slowly, but it does get to infinity. So like, for example, if I did log of a big number here, it won't be that big. It's like 29, but if I add in another 9, 32, it does actually grow. It just grows really slowly. Okay, so a rough sketch of this. Note that e to the 0 is 1. So what that means is on the original function, if you look at it like that, it's 0 in, 1 out. So the 0 here is y. I appreciate this is a bit confusing. So if you flip the other way, it'll be 1, 0. Log x grows very slowly. So for example, log of 100 is 4.6, while log of 1000 is 6.9. The log function grows slower than any polynomial of degree greater than 1. So like even a line will eventually dominate log of x. So if this is log of x, now it just slows down, but it does get there eventually. Any line will eventually be bigger than it. Okay, so basically what you need to know, and it will be written in a summary at the end of this lecture, you need to know the order, basically from slowest growing to fastest growing is what we're talking about. Okay, and you might have a question like this: list the following functions according to how fast they grow from slow to fast. So if it's a sum, the fastest terms dominate. Now 3 to the x doesn't look like an exponential, but it is. I'll just show you here because I probably should have done this earlier, but 3 to the x is in fact equal to e to the log 3 all to the power of x, because e to the log 3 is just 3. And so repeated powers means multiply the powers. So this is e to the log 3 times x. In other words, it's an exponential. And exponentials grow faster than any polynomial. This is a degree 1 polynomial, so this is the dominant term. This one, you've got x cubed, x squared, and x. The highest power of x dominates. So this one. And this one, well, the 6 doesn't really matter. Oh, we can take the 6, it's just this. And then this one, the highest power is the 7x. So I think we're going to write down what they are approximately on the next page. So the dominant terms are in f, it's basically 3 to the x. G is basically 2 to the x cubed. And that basically means that as x gets really, really big, the percentage difference between 2x cubed and g gets very, very small. H is approximately 6 log base 2 of x, and k is basically 7x. So we'll go from slowest to fastest. So you've got the exponential is faster than the polynomials, and the polynomials are faster than the logs. So let's write down logs slower than poly, slower than exponentials. So the slowest here is the h, so the h is much less than. Now we're looking at the polys. Now you've got 2 polys, the highest power is faster. So for small values of x, 7x is bigger than 2x cubed. As soon as x gets anyway big, 2x cubed is far bigger than 7x. So the next slowest function is k, then g, excuse me, excuse me, excuse me. And then the fastest of all is the exponential f. So that's all you have to do there. Another question here, sketch these in the same plane. Now these are actually inverses of each other. Like this is something we've spoken about in the algebra section. So a to the power and log base a are an inverse pair. So now we're only going to do it roughly. Now the log, we know the basic rough shape of the log. We know the 3 to the x is an exponential. That's just our basis. So it wants us to ensure we label each function. We will do that. Clearly indicate the points at which the graphs intercept the x and the y. Well, that's not going to be much of a problem. Clearly mark 2 other points on the graph of each function. Okay, so we know roughly what they look like. So the log, we know, looks something like this. And the exponential, we know, looks something like this. Okay. From here, like this, that's the basics of it. We need to, and maybe there's probably small things. The axis there looks like this, and the axis here looks like that. Okay. From here, we need to make sure we have answered the question that is asked. Okay. So in terms of this one, they both only cut the axis once. This doesn't cut the x-axis, this doesn't cut the y-axis. So this is x equal to 0, y equal to 1, and then because it's an inverse, this will go the other way around. At x equal to 1, log base 3 of 1 is 0. So that's 1 point, and it says clearly indicate. Okay, we've done that. 2 other points on the graph of each, so we need 2 other points. So maybe what we could do here is we could put in maybe x equal to 1 and x equal to 2, I think would be a good idea. I think that'd be a good idea. Into this, by the way, is 3 to the x. This one is log base 3 of x. So if I put in x equal to 1 into this, I get a 3 to the power of 1, which is 3. So I get another point, 1, 3. And if I put in 2 into this, I get 3 to the power 2, which is 9. So from here, we need to make sure we have answered the question as asked. G to the x is strictly positive, so it never hits the x-axis. It hits the y-axis at x equal to 0, and so 0, 1 is in the graph of G. Note that as G inverse is equal to f, they're an inverse pair. 1, 0 is in the graph of that, and so f hits the x-axis there and never the y-axis. 2 other points can be looked at G to the 1. So this is kind of just what we wrote up there. G of 1 is equal to 3, and G of 2 is equal to 3 to the 2, which is 9. And inverting, so this gives you 1, 3, 1 in, 3 out, and 2, 9, 2 in, 9 out are in the graph of G, or in G. Okay, inverting, we get 3, 1 is in F and 9, 2 is in F. So we could do our rough sketch. Not only has to be rough, to sketch them. So sketch doesn't have to be perfect. So let's do our log. Now we want to kind of go up to 9, isn't it? So I'll put 9 there, and I'll put 3, and I'll put 1. And I need to go up to 9 over here, don't I? Yeah. So 9, 3, 1, and I want to label these nicely. So my log goes through the point 1, 0, 3, 1, and 9, 3, 9, 2. So this point here was incorrect. Should be slow down. Yeah, so actually I was doing fine. So the 2 is here. And here you get this thing where the log grows slowly. So I get something like this. That's the log. So the log is called f. So y equals f of x. And now let's do some points on the g. So the g, we have 0, 1. We have 1, 3. And we have 2, which is now here, 9. There's probably a few other options, but this is what you're talking about. And the graphs, you can get one graph from the other, but they kind of have a symmetry. The symmetry through them, I think, is something like, well, I won't write it down because I'm not sure, but I think it's something like x equals y. So that's that question done. Okay, now here's your big remark about if you're into algorithms, why are we actually talking about this thing? Why are we talking about functions growing slow and fast? If that is of interest to you, have a look through this. You might find this for yourself. Okay, the absolute value function. Now the absolute value function is something that you've known before. Like you know that, say, the absolute value of minus 2 is 2. I don't think you've ever seen it written down as a formula and be written like this. So the absolute value of x is equal to. So there's two things. There's two things that can happen. You can give it something positive, in which case you get out the same thing again. So I think, do I have an absolute value function on this? No, you see some calculators with it. No. Anyway, you know that the absolute value of 2 is just 2. So the absolute value of x is x if x is bigger than or equal to 0. But here's the interesting thing. If x is negative, the absolute value of it is minus x. Now that might seem a bit weird. You say, no, but the absolute value makes it positive. Hang on. What's the absolute value of minus 2? We all agree that this is plus 2. But what is plus 2 equal to? Well, it's minus minus 2. So if the thing in here is negative, the absolute value of it is minus the input. So that's where this minus, it's making, if the thing originally is negative, it's making it positive. We can draw the graph of it. I don't think the graph is too important, but basically it's two lines. So if x is positive, it's just x. Now that's like a 1x plus 0. So it's a multiple of x plus a constant. It's a line. The constant is 0 and the slope is 1. It looks something like that. Whereas on the other side, it's minus x, which is minus 1x plus 0. So it cuts at 0 as well, but the slope is minus 1, which is negative. So you get this kind of spiky graph here. Okay. If you know the graph of a function, the graph of the absolute value of the function is easy to draw. You just take the negative bits and make them positive. Okay. So we'll do an example of that. So say if you got a function here, this is supposed to be y equal to f of x. Then the graph of its absolute value, it gets the same thing when the function is positive, but when the function is negative, you make it positive. So like that, those two distances, I know they're not, but they should be the same. It was, say, minus 3, the absolute value becomes plus 3, and then it just continues on its way. So the black function here is y equal to absolute value of f of x. Okay. Now some of these are actually kind of difficult to write down. So the round-down function. So let's see, this is kind of a weird function. So the floor, it can be written, so the floor function of x, which is also written like this, right? It is the smallest integer. Okay, it's the smallest whole number that is less than or equal to x. So that's a weird thing. So it's the smallest whole number less than or equal to x. So for example, the floor of 2.3, what's the smallest whole number smaller than 2? 2.3 is 2. The floor of 2 itself, well, it's less than or equal to, so the floor of 2 is 2, and the floor of minus 4.6. Now, the smallest whole number smaller than minus 4.6 is in fact, you can pause the video and guess, minus 5. Okay. So similarly, the this should be the maximum, sorry. So it's the biggest whole number smaller than, yeah, sorry, that should be max. Ceiling, rounding up. So this was written maybe ceiling of x, which is equal to, we write it up, you round up of x, is equal to the minimum whole number that is bigger than or equal to x. So for example, we'll do the same thing. So the ceiling of 2.3 is the smallest whole number that's bigger than 2.3, that would be 3. The ceiling of 2, what's the smallest whole number bigger than or equal to 2 is just 2. And the ceiling of, say, minus 4.6 is the smallest whole number that's bigger than minus 4.6, that would be minus 4. You probably need to visualize a number line for the negative ones and think about smaller as being below and bigger as bigger. Okay. So these are obviously important functions in computer science because you're always often going to be rounding in that. So here's an exam question. Define a function, a real valued function. Oh, it's worth saying the range of these is z. So every whole number is hit, but only whole numbers are hit. Yeah. So calculate the floor of f of 3 and the ceiling of f of 3. So f of 3 here is equal to 3 over 2, which in decimal notation is 1.5. So the floor of this is equal to the floor of 1.5. Floor just means round down. We won't talk about maxes or mins. So it just means round down 1. And what is the ceiling of f of 3? Well, that is the ceiling of 1.5, just means round up. But you don't round up 2 to 3, round up 2 to 2. Okay, so they're floor and ceiling. And that's pretty much all these examples. So now we'll go through, there's a lot of exercises here, which are good exercises as well for functions. We'll go through them. So prove that f is not onto, probably the best thing here is find, that's going to whole numbers, a whole number that is not hit. Now note that the inputs are whole numbers as well. Inputs are whole numbers as well. Okay, is it now let f go from reals to reals? Is it onto or not? I recommend sketch the graph. And then what you can do is you can use the horizontal line test. Consider this function, okay. Write down the ordered pairs, okay. Graphically represented using an arrow diagram, that should be okay. Is the function invertible? Well, think about 1 to 1 and onto. Right, the graph and the diagram matches which of these. So I would recommend looking at t equal to 0, and note that at t equal to 0 you must get out 10. I think we did this question in the thing, yeah. Okay, here's the graph. Oh yeah, these were done already, so throw these out. Sorry about that. Below there are 7 lines plotted. Match the lines to the graph. So remember that L of x equal to mx plus c. This is the slope. If it's positive, it goes up. If it's negative, it goes down. And the c is where it cuts the y-axis. That should be enough to answer that. Below c, I plotted the graphs 1 plus e to the x and e to the 2x. So what I'd probably say here is there's 2 options. You could look at maybe x equal to 0, but I think it's better to look at growth rates. There's probably going to be a chapter summary at the end of this. It might be worth that'll summarize some of the growth rate stuff. So this is 2 ways to answer this question. Below see a plot of these 2. Label appropriately. I would have to say you have to look at growth rates. Log of x, I think your best bet here could be either look at x equal to 1 or again growth rates. Complete the following. Circle the function that corresponds to this graph. This is a good question. I think you probably need to rule out. You can rule out 3. Okay. And then and then what you want to do is maybe look at x equal to 0. Maybe here you can rule out 1, 2, 3. Yeah, I think it's the same advice. Here you can rule out, I think you could probably rule out 1, 2, 3 and then look at x equal to 0. Same advice. This one, I can rule out, it's hard to rule out things here. You can rule out only 2 maybe. And then I think the easiest thing probably is to look at x equal to 0 as well. Okay. This one is probably the easiest. Okay. All right. Here's a question that was kind of hinted at the notes. So remember, it's a rough sketch, and all you're saying is that there's 3 possibilities for this m. Is that it's plus, it's 0, or it's negative. Yeah. Now this question is about solving y to L of x. So this is y equal to mx plus c. So, and then solve this for x. Okay. And the question is, so the algebra from the previous part appears to give a formula for it. So it appears to say that y to mx plus c is always invertible no matter what the values of m and c. Explain how this formula is not valid when L is not a bijection. So that's a hard question, but you're linking these 2. The algebra here with what you did earlier. Produce rough sketches. Now again, it goes back to thinking about y to mx plus c. Here you're thinking about, I probably only want to consider 2 bits. So there's 3 things maybe. The rough shape, x equal to 0, and growth rates. So basically the rough shape, you want to, like say for example, e to the x, I know it looks like that. X squared, I know it looks like that. Then I'll look at what happens at x equal to 0. I know at x equal to 0, this is equal to 1, and I know at x equal to 0, this is equal to 0. So I get these points, and then I say which one grows faster. So I know that this one grows faster. So I incorporate all of this into a picture, but I make sure the e to the x is biggest after a while. Okay, so here floor function does it. First one is saying, is it onto the whole numbers? Does it hit every whole number? Does it hit every real number? for example, is a half in the range of floor. Okay, these are pretty straightforward. Produce these. Oh, this is a hard question. I'll let you kind of think about it. So probably what I'd probably do is I'd separate. So this is the absolute value. That's probably the easiest one. It's kind of directly done in the notes. But the rounding down and the rounding up, I'd probably break it into, for these two, look at this region, then look at this region, then look at this region, then look at this region. That's a wicked. It's a very difficult question actually. It's nice but difficult. So basically the idea is, yeah. So what I'm doing here is here you're looking at y between 0 and 1. In this region, y is between 0 and -1. In this region, y is between -1 and -2. Here, y is between -1 and 0. Here, it's between 0 and 1. And also look at between 1 and 2, 2 and 3, and 3 and 4. So break up the graph like that. List from slowest to fastest. Okay, we're going to look at that. You look at the summary to that. Summary. And summary, which will be the next video. Yeah, I don't have time for this now, so we'll go to it.